Welcome back, trigonometry, to another exciting video with C-squared mathematics. I'm Mr. Carlson. You just finished the basic trig quiz. And so now what we're going to be doing is reviewing that quiz, but only a couple questions. I have some honors questions on there as well. So we'll go through that. We'll go through the lesson, 5.4 unit circle. This is a big, important lesson. Is it like big, like long? No, it's not long, but it's just a very important and fundamental lesson. So if you're going to watch any video this week, I definitely encourage you to watch this one, although I want you to watch all of them. Let's get started. These are the 4 questions I have for your bell work. Again, they're taken directly from the basic trig functions quiz. These are 2 regular questions, but they'll more than likely be on the homework. Sorry, not the homework, but they were on the quiz. So make sure you review these if you're regulars. If you're honors, doesn't hurt, right? To just go through it because it doesn't hurt, and it probably does help. These are the honors questions, though, right here. So please, if you're honors, at least review these because some of you did miss those. So if you need to, pause the video, get them down, and then we will get started. The first one is use reference angles to find the exact value. Now notice how it says the exact value. It doesn't say just find the reference angle. If they said find the reference angle, then we would just be finding an angle. But they want the exact value, which means they want this evaluated. They want a side length. So there's a couple ways to do it. Usually what I do is I would draw you your XY plane. I would break it up in fourths because it's pi all over 4. So what this is saying is 31 pi all over 4s. And so then I would just count 31 different times. Now, I could definitely do that, and that's usually how I showed it in the past. I want to show you a new way, a way that kind of correlates to what we're going to be doing here today. Okay, so I'm going to erase this. I'm still going to be kind of doing that just slightly, but just different. Okay, I'm going to be doing it just a tad bit different. So before I do that, though, I want to just look at this angle. Just look at the 31 pi all over 4. Now I'm going to do some arithmetic on this. How many times, I'm going to ask this, how many times does 4 go into 31? Well, you'll say 7, because 7 times 4 is 28. So it goes into 31 evenly 7 times. Okay, so watch this. What I'm going to do now is I'm going to take cosine, and what this is going to be is 28 pi all over 4, which does equal 7 pi, right? This goes into it 7 times, but plus, what's the remainder? If 4 goes into 31 7 times, and that equals 28, how many more pi's do I have? Well, I have 3. I have 3 pi's all over 4. 3 pi all over 4. Now here is something that we're going to be doing slightly today, but I wanted to show you it now because you already kind of have the precursor, the foundations for it, the preview for it. So what does this mean? This means this right here is going to be equal to 7 pi, because 28 divided by 4 is 7 pi, plus 3 pi all over 4. Now this tells us a little bit better of how many times this goes around the circle. How many times does it go around your XY plane? Now, if it's 7 pi, think about it even more clearly. How many times does it go around the XY plane? How many times? Well, if it's 7 pi, and then 1 revolution is 2 pi, then how many 2's can I put in here? Well, I can put a total of 3 2's, because 3 times 2 is 6, right? So let's break it down even more. Ready? So cosine, so then this is 6 pi plus, because 2 pi times 3, it goes around revolution of full 2 pi, and then I take that 2 times 3 because there's a total of 3 2 pi's in 7, okay, which equals 6 pi, but then what's the remainder? Again, we come to 1 pi, and then this right here, 3 pi all over 4. Now this is very interesting. Why? Because now what we can see is if we add all of this together, we do get 31 pi all over 4. What we just did was we've reversed the process. And I think that's fascinating. Why? Because it helps us solve it faster. You may not think it does, but the more practice you get to it, the more it does actually help you solve it faster. How does that help you solve it faster? Well, think, guys, think. This is 6 pi, which means it goes around 3 different times. So if it goes around 3 different times, I want to find the reference angle and ultimately the exact value. Do I care really that it went around 3 times before I actually figure out what this value is? The answer is no. I don't care whether or not it goes around total 3 different times because 6 pi is a total of 3 revolutions in the full circle, right? I don't care because it's going to be what we call periodic and it's going to continue through the season. I already know it's going to go around the 4 quadrants over and over and over again, and it's going to stop where it left off. So it really didn't do anything for me. Where I want to know is where this angle, guys, where this angle is in the quadrants, okay? Yes, I can probably plug this in the calculator, the TI-36X Pro, absolutely. I can't plug it in the Desmos, it gives me a decimal, okay, unless you know what the radicals are in the decimal version. But if I really want to solve this straight up by hand like I am, I need to know, in order to find the reference angle, sure, I already know what the reference angle is. It's pi over 4 because it's 31 pi over 4s. But what's the exact value? In order to know that, I need to know which quadrant. And so this is why I'm doing this, guys. I need to know which quadrant this value is in. Now, you could change it to degrees and keep going around and around and around, sure. But this is kind of a fast way to kind of break it down saying, okay, I really don't need the 6 pi because it's just going to go around 3 times. So now when I go to my actual XY plane, what this is saying is, okay, it went around 3 different times. I can skip all that jazz and just go straight right here, okay? Because I know it goes around 3 different times, but it comes back to its original position. Now, if I add another pi, which is that right there, but then add an additional 3 pi all over 4. That's three segments of quarters. So if I break this up, 3/4 of a whole. How about that? If I break that up, okay, this is 1 pi all over 4. This is 2 pi all over 4. And this is 3 pi all over 4, which means this goes an additional 3 pi all over 4 into this quadrant, okay? Wow, that arrow is kind of obnoxious, but it goes into that quadrant, okay? Now what we can do, okay, I'll actually make this a little bit blue. Now what we can do is actually build our triangle. I know now my reference angle is, in fact, pi over 4. Now, it's great, but did it ask for the reference angle? No. Okay, that's great that we know it, but it didn't ask for it. What it wants is the actual exact value. So what's the exact value? Well, I build my pi over 4 triangle, my 45 degree triangle in quadrant 4. So this is 1, this is 1, this is 2, but I need a negative here because it goes down. Remember, this point right here would technically be 1 comma negative 1. Goes over and then down. Okay? So now what we can finally do is ask, all right, what is cosine of 31 pi all over 4? What is the actual exact value? Well, what's cosine's ratio? Opposite? No. Adjacent? It does, but then over what? Over hypotenuse. So ka toa. So adjacent, which is 1, over hypotenuse, which is, oops, sorry, this is radical 2. Don't forget that. This is radical 2. And then this simplifies down to radical 2 all over 2. If you did this on the TI-36X Pro, you would technically get this, yes. As long as you're in radians, of course, right? Awesome. So this is how you do it completely by hand in almost a new way. And I love that. I keep finding new ways every single time I teach trig. I keep finding new ways to sort of teach the math, and I love that. There's so many different ways to teach trigonometry. So I hope that sort of makes sense. If you do need additional help with that, then please let me know. Let's erase and let's go through the other ones a bit more quick. So this one is something that we've went through our notes constantly over and over and over again, but we're going to go through it again. We see that tangent is negative, and then sine is less than 0, so that's also negative as well. If it's less than 0, it is negative. So my first step here is going to be, okay, find out which quadrant it's in. So all students take calculus. Which quadrant is this in? Well, it can't be the all, because clearly we have negatives and all functions are positive there. It also can't be in the tangent one because tangent's negative and only tangent's positive there, so it can't be in the third. Now, sine is negative, which means it can't be here in the second, because if it's there in the second, sine would be positive, but it's not, which means it's in the fourth quadrant. So now going to my second step, I'm going to blow up my fourth quadrant here so I can kind of see it a bit more clearly. And now we can start building my triangle. Okay, do I care what theta is? No, I do not care what theta is. They just want the exact value. Okay, I do not care what theta is. So the exact value of theta, I don't care about, but the exact value of my actual side lengths, I do care about. What are they? Tangents ratio is opposite over adjacent. So opposite 3 all over adjacent 5. Which one gets a negative? The 3, of course, because it goes down. So this point right here is technically 5, negative 3. Now what's my R value? My radius here. My radius, it's just something, okay? How do I find it? Pythagorean theorem, of course. So this is 25, then plus 9, and this equals, not plus, equals R squared. So this is 34, and then R squared, and so R equals radical 34. Awesome. Okay, my third step, and probably my final step, now I can finally get my remaining trig functions. What's sine? Well, sine of theta is opposite over hypotenuse, so negative 3 all over radical 34, which is negative 3 times radical 34 all over 34. Notice how it's negative, and we're in the fourth quadrant. Now, if we're going to do cosine, is it going to be negative or positive? It should definitely be positive. So 5, because that's my adjacent, all over my radius, which is the hypotenuse, radical 34. So this simplifies down to 5 radical 34 all over 34. Okay? And then the other ones we can just switch. So cotangent is probably the easiest one, just negative 5 all over 3, just from what we're given right here. Okay? And then we can do cosecant theta. I'm going to switch the unrationalized version, so negative radical 34 all over 3. Still keep the negative. And then secant, of course, is still going to be positive, but I switch to the unrationalized version. And so this is radical 34 all over 5. Perfect. That is all 6. 1, 2, 3, 4, 5. And then 6 is what we are given. Okay? So I went through that pretty fast just because we went through it a lot on the last video. And so I'm going to leave it like that. If you have any questions, please just email me. Now, these are going to be the trig honors questions. I'm going to go through these, hopefully not as fast, but faster. And the only reason why I'm going to do that is because I would like to get to the lesson. Okay? So what does this say? F of theta equals 2 cosine theta plus sine of 2 times theta. So when I do f of pi all over 6, what this means is 2 times cosine of pi all over 6, and then plus sine of 2 times pi all over 6. That's the tricky part right there. Okay? So what is cosine of pi all over 6? Well, that's going to be radical 3 all over 2. We can do that on the calculator. Even though it says not to use a calculator, we can just use a triangle if we really needed to. So this is pi all over 6. This is cosine. So this is 1. This is 2, and then radical 3. So cosine is radical 3 all over 2. Okay, and then plus sine, well, this needs to be simplified, so that goes poofy and this becomes 3, so this is sine of pi all over 3. And then we simplify a little bit more, the 2's go poofy, this is radical 3. Now this is pi all over 3, so we can do the exact same thing. If this is pi all over, if that's pi all over 3, what's the opposite side? I think I told you guys a trick of mine is if this is pi over 3, the opposite side is always going to be radical 3 because its 3's are opposite of each other, so that helps me. And then this is going to be 2. This is obviously 1. And so what's sine? Radical 3 all over 2, opposite over hypotenuse. So radical 3 all over 2. And then times 2, which I know we just kind of did that already. Kind of sucks, but this is technically 1 radical 3, that's 2 radical 3, so when we combine them, it's 3 radical 3 all over 2. And that is my final answer. Yay! All right, let's erase. Now this one, again, is another honors question. I'm going to go through it pretty quickly. So we want a function of sine of x, and so it gives us a bunch of function notation. We don't want to use a calculator, so I'm not going to. What is this? I need to simplify this before I do anything. So this is times 2, gives me 6 times 2. So this is 5 minus 2, which is 3. So my function is actually 3 pi all over 6, which reduces down to f of pi all over 2. And now what this actually equals is plus, and then we have f, and then this is 5 pi all over 6, and then this is plus f of pi all over 3. Okay, what does this mean? This means sine of pi all over 2 plus sine of 5 pi all over 6 plus sine of pi all over 3. Now most of what you should have in your notes is that this is a quadrantal angle, this is a special right angle, okay, and this is something different. So let's kind of come back to these because we should have pi over 2 and pi over 3 already in our notes. Now this, 5 pi over 6, is just going to be in the second quadrant. We need to build what that is. So remember, we would look at 5 pi over 6, okay, and then this is saying 5 pi all over 6's, which means my reference angle is pi over 6, but which quadrant is it in? I need to know which quadrant it's in order to evaluate it. So we break it up like this so that we can go and start, counting. Remember, pi over 6 is 30 degrees. Okay, so there's 3 sections in each quadrant of 30 degrees to make a 90-degree quadrant. So that's 130 degrees, 130 degrees, 130 degrees. So that is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So we're right here. We're in quadrant 2, which means I'm going to blow up quadrant 2 real quick. And we're going to see what this is. What's my reference angle? We already said it's pi over 6. Okay, that's my theta. Now we just need to build the triangle. Okay, so this is 1, this is negative radical 3, and this is 2. Okay? Why is it negative? Goes to the left. Why is that positive? Goes up. And then r is never negative because it's technically distance. Okay? So what's sine? Opposite over adjacent? No. That is definitely tangent. Is adjacent over hypotenuse? No. That's definitely cosine. What it is opposite all over hypotenuse, so 1/2, which means we can start building this. So I know the middle term is 1/2. This should be 1. That's taken directly from your notes. If you don't know that, it's right here. So it's a quadrantal angle because this is pi all over 2, but this point right here is 0, 1, and we said it was that value, 1. And then plus sine of pi all over 3. What's sine of pi all over 3? Well, again, if we kind of look at our notes, we would know that this is radical 3 all over 2. Now, of course, we need to do an order of operations. So this becomes 3 because 2 plus 1 is 3, and then plus radical 3. And then, of course, everything's all over 2. And that is my final answer. So it is an exact value. If you did plug this into your calculator, you should get something like this. Hopefully I didn't do it wrong because I haven't seen this question in a long time. So if I did it fast and I did it wrong, well then, you know what? Oh well. I'll just have one of my students comment in the section below, and they'll tell me I'm wrong for like the 100th time. Okay, let's get started. All right. Now, to kind of finish bell work off, let's review some of my quadrantal angles, some of our quadrantal angles. Now remember, our quadrantal angles, if I have an XY plane, are right here. Okay, these are my quadrantal angles. Now, if you remember last week, this point was, this point was 1, 0. So this point was 1, 0, and this was 0 and 360 degrees. This point was 0, 1, and this was 90 degrees. This is 180 degrees, and this one was negative 1, 0, and this was 0, negative 1, and this was 270 degrees. So these are the quadrantal angles, okay? Now, here's the question, okay? It is because r equals 1 that we could do that, because right here we can see if r equals 1, this is 1, this is 1, this is 1, this is 1, okay? They're all 1, right? That's why we have 1s in our ordered pair, right? So they're all 1s. Now, I only asked for 0 radians and pi over 2 radians, and this is pi over 2, and this is 0 radians. But I wanted to do the whole points. I wanted to label all the points, all the quadrantal angles, and everything. Now, you should already have something like this in your notes where you filled out what we call the Trig table of common angles. Now, I'm going to give that sheet to you today. By give you, I mean it's going to be on Google Classroom, okay? The whole key is going to be on Google Classroom. Feel free to copy it down, print it off, but I highly encourage you to take the time to at least print it off or copy it down, take a picture so you can have it on your phone or whatever, okay? If we were in class, we would actually copy it down and everything, and you would do the whole thing by hand, but we're not, so I'm giving you the key, okay? So you don't really need to worry about that because you will already be given the key. But I just want to remind you that this is what it looks like. And here's what I also want to remind you. Watch. What does this look like? If I go from that point to this point to this point to this point. Maybe it looks like a lemon, okay, but it should look like a circle. Okay, it should look something like a circle, and it can go around and 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 around infinitely. Okay, what do we call that circle? We call that circle the unit circle. And so what we're going to be doing is defining and finding trig functions on what we call any number, any real number. Which means because that circle can go around and around and around and around and around literally infinitely, we saw even on the bell work that we can kind of break that apart and find that reference angle within that large angle, right? So this real number really does help us when it goes around infinitely over and over and over again. That's what I mean by trig functions on any real number. Okay, I can now kind of branch out. And I don't need to do anything with my I don't need to do anything with my special right angles. I can use my special right angles, but I don't need them anymore. Okay, I can use them, but I can really just kind of jump the gun and use what we call the unit circle. I'm going to show you how that works. And then how does the unit circle aid in solving trig functions? It aids because you can just glance at it and you know that you'll always have the right answer. You don't need to use a calculator anymore. You don't need to use your tables anymore, your actual drawing and going around and around like we did during bell work. You can now utilize this one big fat circle in order to help you solve for some of the basic trig functions like sine of pi all over 3 or sine of 5 pi over 6, or cosine 11 pi over 6, or tangent of 3 pi all over 2. Your unit circle, your trig table of common angles will help you solve that, okay? So right here, I'm going to have a brief intro. Like, what are we really doing? Well, I'm going to kind of put it all together. I'm going to show you what the definition of the unit circle is. I'm going to show you then the trig definitions of the unit circle. We're going to go through 2 examples, and then we're actually then going to go to the unit circle and see firsthand on Desmos how this is even built. Because if you can't build it in class for me, and if I have to just give it to you, I'd rather go on Desmos and show you at least throughout the video how it's built, okay? So the first thing that we did about a week ago, 2 weeks ago, we first defined trig functions using a right triangle. I mean, that's what we did 2 weeks ago, right? You did this in geometry. I mean, like, this is geometry, okay? But we were limited to what we call acute angles. Now, in geometry, you use just degrees, and in trigonometry, we use radians, right? So we are limited to just what we call acute angles. And then in 5.3, we defined the trig functions using the coordinate plane. We took geometry and algebra and wed them together to make trigonometry, okay? And that's where we got the x, y, and r formulas. That was 5.3, trig on any angle. We could use any angle, and by using any angle, we use what we call reference angles in order to find what that evaluation is. Okay, but now what we want to do is evaluate any trig function on a real number, for any real number, really. So we want to evaluate trig functions for any real number, and in order to do that, what we need to use is what we call the unit circle. Now, first off, why is it called the unit circle? Okay, the unit circle, the reason why it's called a unit circle is because it doesn't matter the unit that you're in. You could use it for feet, inches, meters. It doesn't matter. It will work out no matter what. Okay, it will always work out, and that's the beauty of it. Okay, it will always, it's resilient. Okay, it can stand the test of time. It's beautiful. So as I said, we'll start developing this circle here, and you see this circle. Now, what is some of this stuff? Okay, you have an xy plane. Now your r right here is 1. Okay, so r equals 1 here, but what is this t? Okay, I'm going to show you what that is. Now, if r equals 1, that means theta equals t. So that means arc length equals t. Now, why is that? Remember our arc length formula, okay? Before we get to the equation of this, my arc length formula is r times theta, okay? Now, if my r is 1, and then I times theta, right? And then theta equals t, so that means s equals 1 times t. That means s equals t. Now, what is t? T is technically that any real number. So any, and now I'm going to use my fancy real symbol here in mathematics. It's just double-lined r. So any real number. That's really what it means. So it could be any angle. Okay? It can be any angle at all. That's what it actually means. I can go round and round and round and round and round and round and round like freaking Rosie Posey. Okay? And then I can still find out the exact value of the trig function regardless. We even did that in our bell work when we said cosine of 31 pi all over 4. This is a rather large number, but what we did was we went around 3 times, then an additional time, okay, and then one more. So we went around 3 times, 1, 2, 3, an additional time for just pi, and then a couple more. And then we had it right here. That's a lot of around and around and rounds, right? But we did that just basically because we can utilize what we call reference angles, but we also, because I taught it to you like that, we also utilize what we called periodic functions, okay? And we're going to learn more about that in a little bit. So what's the equation of this? The equation of this circle then, if r equals 1, and if it's a circle and the center is 0, 0, the equation is straight up just x squared plus y squared equals 1. This is my equation of a circle. Okay? Now here's a question. What happens to our trig functions when define them on any point? What happens? What happens to our trig functions when we define them on any point? And how does this relate to our trigonometric identities? Here's the question. And I kind of already explained it to you. So boom, I have that. But here, think about this. Given that P of x comma y, what does that mean? This point right here. Okay, I can build my triangle. Okay, this is x and this is y. And this is r, right? This is r right here, technically. Okay, that's r. Now think with me. We kind of already did this in 5.3, okay, but think with me. If I want to now find what cosine of t is, what is cosine of t? Well, cosine of t is x all over r. But if my r is 1, that means my radius is 1 on this circle. That means it's just x all over 1, which just equals x. Right? So that means cosine is just my x. And then sine would be y. Look at my angle right here where I'm kind of twiddling my marker. Sine of t is opposite, which is y all over r. So this is y all over r. Okay, which is y all over 1 because r is 1, and this just equals y. What's tangent? Well, opposite over adjacent, so y all over x. So tangent here, tangent of t equals y all over x. Now, I already explained this, if you watched it, if you thoroughly watched the video in 5.3. What is the trigonometric identity for quotients involving sine, cosine, and tangent? Our trigonometric identity is tangent of theta equals sine of theta all over cosine of theta. Okay, that is our trigonometric identity. Yes? Now watch this. Tangent is y all over x. Tangent is sine all over cosine, right? What's y? Sine. Sine equals y. What's cosine? X. Cosine equals x. So, what's tangent? Y all over x, or in other words, our trigonometric identity, sine all over cosine. Okay? And we can flip this too. Watch. So let's do cotangent. Cotangent of t is just a flip, right? So x all over y, which means my trigonometric identity, man, I keep getting cotangent and cosine mixed up. My trigonometric identity is cosine all over sine. So x all over y. Cosine x all over sine y. So these are how the trigonometric identities actually came to be, by the way. And now we learned them way before we learned this, the unit circle. But I just want to reiterate the fact that mathematicians just don't just come up with this stuff like, this seems right. I guess this is true. No, like we actually prove it out. We start with the foundations and we go through the foundations and we start building upon building, just like any builder. When you're creative enough, you build things from scratch. You start with a foundation and then you build up from there. Sometimes you have to take things apart and then put new things back together. Okay? That's what a builder does. That's what any good professional does in their career. And that's what these mathematicians have done. They looked at the very foundations of what it means to be a trig function. And then they put the trig, the geometry, with the algebra. And because they started seeing these triangles and it goes around in a perfect circle, then they started saying, okay, that's x, that's y. What if it's 1? Okay, well, that's y all over r. Well, that's y all over r. Okay, well, y all over 1 if r is 1. So sine is therefore y. So this therefore is true. And if that's true, we can then build these identities. And that's exactly what they have done. Why is that important? Because next week is your test, your Unit 1 test. And after that, we're going to be starting. I don't want to freak you out, but I'm just going to say it how it is because I love you and I care about you guys. We're going to be starting the hardest 2 weeks in trigonometry that you will see. The hardest 2 weeks. They are hard. Traditionally, students find those 2 weeks very difficult. They have names for them, fun names I won't say on this video, but maybe I'll say it during our Google Meets. But they have fun names for those 2 weeks, okay? Colorful names for those 2 weeks because they're very difficult. okay? But I personally find it amazing because it connects the foundations like this to the actual trig, the actual like what the actual trig is. Okay, you're building foundations. So after that spiel's done, because I didn't want to spiel, but I spieled anyways. What does that mean for us? It means we get new definitions. Isn't that exciting? Okay, we get new definitions. Now, we already kind of did this in the last slide. We did that in the last slide. We even did that in the last slide. And we even did cotangent in the last slide. Now, the reciprocals aren't really that needed, is what I'm saying. Like, the reciprocals aren't really that needed. What's really needed is the main trinity of trig functions, and that is sine, cosine, tangent. Okay, so if t is any real number and p equals x comma t, so your normal point, x comma t, x y, or sorry, x comma y, your normal point, x y, that is the point on the unit circle that corresponds to your angle measure, t, then boom, this is what I have. Okay. Now, if none of this makes sense to you, that's okay. It didn't make sense to me when I first learned it. But once you go through the examples, it at least teaches you the very basic structure of what's happening here. What happens is now we're getting new trig functions in terms of the unit circle. Okay, we're getting new trig functions in terms of the unit circle. And what that means is that now sine will equal y, my y coordinate, cosine will equal x in my x coordinate, and then cotangent is literally just sine all over cosine, my y coordinate all over my x coordinate. That's what tangent will equal. Okay, and so I want to reiterate that that's what it is. And then tangent, obviously, x cannot equal 0 because then the world would explode. So let's kind of see what this looks like in real life with just some basic examples. Okay, 2 examples. And then after those 2 examples, we'll actually get through what we call the unit circle. How is it built? And that'll give you time to kind of explore the unit circle using Desmos and then also on Google Classroom. Okay. After that, we'll get to our actual lesson of what it means to be a periodic function in trigonometric functions. So this is something that you'll see on Math Excel. T is a real number equal to the length of the intercepted arc. So that you notice right here, we said S equals T. So this is technically S, but now we don't write S because we said S was equal T if this equals 1, right? So if my radius right here equals 1, so R equals 1, that means, just reiterate again, this would be 1 times theta, but my theta is t, so that means S equals t, the central angle, which means now what I can do is just write t. If that's the case, okay, I have R equals 1, my central angle is t, and then my intercepted arc right here, my actual length of my circle is itself also t. Okay, it's also whatever that angle is. Okay, so if my angle right here is like, 120, then that means this t is 120. Okay, but it could be inches, it could be meters, it could be whatever. It doesn't matter. Okay, that's why they call it a unit circle. That's what's so important about it. So let's get to our actual problem. If this is my point, p equals -1/2, comma, radical 3 all over 2, okay, figure out what the trig functions are. And honestly, guys, it's very simple. Ready? So sine of t equals, ready? If we said sine of t equals y, that means it's just my y coordinate, which means it is just radical 3 all over 2. That's it. You're just looking at the point. Now, if we said cosine of t equals x, that means it's just my x coordinate, which is just -1/2 all over -1 all over 2, so -1/2. And then if I want a tangent of t, it is literally my x, radical 3 all over 2. Sorry, my y, radical 3 all over 2, all over my x, which is -1/2. The 2's go poofy, and then I'm left with radical 3 all over -1, which is -1 times 3, radical 3. So negative radical 3. Okay, so we already know these functions a little bit, By a little bit, I mean they look like our special right angle functions, like there are evaluations. And honestly, you're right. They look like our special right angle evaluations, and that's the purpose. Okay, so this example is really just to show you, one, how easy it is now to just evaluate these. If I have a point, I can just look at my x and my y, and then I can at least do the 3, and then of course I can do the rest by just the reciprocals, right? And that's the purpose of it. Okay, so let's go to another example, something that doesn't really, that should be almost very, very similar. Okay, almost exactly similar. So you have something like this. Okay, now what does this mean? This means it kind of goes around a couple times. Okay, it kind of goes around a couple times, but what it really means is you're still your outside arc length is equal to your inside uh, central angle. But I don't really care about that because this is really all I'm looking at right here is these points. So if I want to know, find the values of the trig functions at t, all I have to do is look at those points. This is x and that's y. So what is sine of t, my y coordinate, which is radical 2 all over 2? This one right here, my y coordinate. What's cosine of t? Cosine of t is the exact same thing, radical 2 all over 2. Why? My x coordinate. What's tangent of t? Tangent of t is y all over x, or sine of t all over cosine of t, because that's my quotient identity, which is therefore radical 2 all over 2 divided by radical 2 all over 2. The 2's go poofy, and I'm just left with radical 2 all over radical 2, which equals 1. Or you could have just said radical 2 all over 2 divided by radical 2 all over 2. It's the exact same thing. And the exact same thing divided by itself is just 1. Okay? Okay, so that wraps up this problem. I'm going to erase. And now what we're going to be doing is actually getting into the unit circle. So if we were in class, what I would do is actually give you the unit circle. I would have you guys complete it. I would have you guys complete the actual trigonometric table of common angles. Obviously, you're not going to be doing that, and so I'm not gonna make you guys do it by hand. I'm actually going to give you the keys. So first, before we actually get to the unit circle and what it actually looks like, I'm just going to show you. If you go to Google Classroom, if you go to classwork, and then down here on classwork, okay, down here in classwork, you will see something that's called the trig table, unit circle, and the trig table of common angles. You'll see something like this. So first of all, the unit circle looks like this. Okay, if you were taking algebra 2.2 with me last year, you would have seen this. Okay, you already see this. I've given it to you, the key. You can print this off if you want to. You can do whatever you want. It's yours to do whatever you want with. Now, you can use this during tests, quizzes, like you can do that, and you can use it during homework quizzes, and perfectly fine. So if the cool thing about this is if it asks you what sine of cosine or sine of pi over 6 is, okay, you can look and sine of pi over 6 is right here, and then sine we already know is y, so then it's 1/2. If it wants you to find cosine of 5 pi all over 6, cosine of 5 pi over 6, well, 5 pi all over 6 is right here in the second quadrant, and then cosine is the x, so it's negative radical 3 all over 2. It says it wants you to find sine of 5 pi all over 4. 5 pi all over 4 is right down here, okay? And sine is my y coordinate, so it's negative radical 2 all over 2, okay? That's how you technically use it. I'm going to continue doing that throughout, and I'll probably reiterate this next time we meet online because I really want to be rejuvenated, and I want you guys to be able to be rejuvenated as well, and so that you already are prepared for this video and you already see what it is, okay? So I'm not going to go too much into that depth, okay? But what I will do is I'll show you the trig table of common angles. This is my key. I posted it for you guys. All right, so this is the trig table of common angles. You can print this off as well if you would like. But what this does is it doesn't just give you sine and cosine, it gives you tangent, cosecant, secant, cotangent. So what's the difference between this and the unit circle? This gives you tangent, cosecant, secant, cotangent. Okay, whereas the unit circle just really gives you the x and the y coordinate, which is just cosine and sine. So you would have to deduce and mathematically figure out what tangent, cosecant, secant, and cotangent is by using your x and y. Okay, which is fine, you can do that, but it's just a little bit more work. What this trig table of common angles is, it already does the work for you. It already tells you what cosecant of pi over 3 is. It's right here. What cosecant of pi, it's actually undefined. What secant of 3 pi over 2, it's also undefined. Or secant of 4 pi over 3, it's negative 2. Okay? They tell you this stuff. All right? So please feel free to print this out to use it during a quiz, test, whatever. Okay, this is what it is. I'm sorry it's that way. I'm having a difficult time trying to flip it because it's not a picture, it's a PDF. So, I mean, and I don't have time to flip it for you. So, sorry, you can print it off yourself. Now, you don't need to use this, is what I'm saying. This is just to help you. You don't need to use this. Actually, when I took trig the first time in college and all the way through my high school, I did not have this. I didn't even have a unit circle. Okay, I didn't even have a unit circle in which I could just glance at. I had to create everything myself by hand. Okay, all the way through high school and trig. Like my teachers weren't allowing us to use the unit circle and trig table. But thank your lucky stars, you have a teacher like me. Okay, where I'm actually allowing you to use it. All right, and so you can actually focus on the trig instead of just focusing on the how it works. I want you to know how it works, and I will teach you right now how it works, but I want you to focus more on what the trig is rather than how the trig works. Okay? I feel like that's more for like college and for other things. But regardless, I will still teach you. If you have any questions on that, please, please, please email me. I want you to email me. Okay? Now, that's again going to be on the classwork. It's going to be underneath a unit circle and then trig table of common angles. Now, what we're going to be doing is going to be looking at these trigonometric graphs. This is the Desmos. If you click on the trigonometric graphs, we'll review the trigonometric graphs, because this week is for graphing. But also, if you click on this, the unit circle, you'll see something like this Desmos. You'll see something like it, not actually like it. I'm going to show you what it looks like in a little bit. Now, what I'm going to do is trying to do an exploration thing. Okay, so you have to bear with me. How does someone build the unit circle? I'll show you how. Just like in our bell work, we had quadrantal angles. Yes or no? You will say, yes, Mr. Carlson, we had quadrantal angles. We started with 0 degrees, right? Now notice right here, I'm at A. Notice also, cosine is x, right? And then sine is y, correct? And this right here is my unit circle. Now you don't see it because I have it blocked, but just watch. Just kind of follow along. Don't even really write it. Just kind of listen. Okay? My angle measure, my A, okay, is 0, right? Okay. Now what if I want to change that to, let's just say, 90 degrees? Okay. Well, notice it's now at my 90-degree angle. That's my quadrantal angle. Okay, great. What if I wanted to change it to 180? Notice how it's right here, right? Perfect. Now, what if I want to change it to 270? Awesome. That's another quadrantal angle, 270 degrees. Notice how I'm also in degrees, 270 degrees. Perfect. Now, what if I want to change it to 360? Okay, perfect. 360. Okay, it's right back where we started, correct? Now, we're back at 0. What did we just do? What we did was we went into a circle. That's what we did. But more importantly, how did we go into that circle? We went from here to here to here to here. And so what we did was we built that circle, okay? And that circle went from 0 degrees to 90 degrees two 180 degrees, okay? And then two 270 degrees, and then finally 360 degrees, and then back at 0, correct? That's what we went. We went around the unit circle. We went around this circle. If r is 1, r squared, r is 1, so if r is 1, r squared is 1, so that's my r right here. Remember your geometry of circles, okay? Remember that. So r is 1, and this totally makes sense. Perfect. Yes? Yes. Now, what happens when I take 30 degrees? 30 degrees. Let's take 30 degrees right there. Whoops. Boom. Okay. That's 30 degrees. What does it look like? Well, Mr. Carlson, looks like a triangle, obviously. Let's build it. Okay? If we built this, let's do it in red. Keep the red and black. I like the red and black. So this angle is, of course, 30 degrees, which in radians is pi all over 6, right? Yes? We know it's a right angle, of course. Now, if we built this triangle, now just follow along, just pay attention. You don't even need to write anything down. I'm giving you this link in Google Classroom. I'm giving you this link. Just pay attention. Okay? This pi over 6 right here, this is 1, this is 2, and this is radical 3, right? Now, this radius is not 2. This is not 2, right? Although this is pi over 6, correct? It's not 2. How do I make it, or it's not 2, because what this actually is 1. Okay, this actual radius on the unit circle is 1. So how do I make this 2 1? Well, I have to divide, of course, by 2 to make it 1. So now it's a radius of 1. But then what do I do now? Well, in order to divide by 2 with the radius, I have to divide everything else by 2. Correct? Yes, Mr. Carlson, that's correct. You have to do that. Which means now my radius is, of course, 1, where one of my legs is radical 3 all over 2, and one of my legs is 1/2. Now watch this. Watch. Now, what is sine of pi over 6? Well, you would say opposite over hypotenuse. Great. So sine of pi all over 6 equals 1/2 all over 1, which reduces down to just 1/2. Right? Now watch. We said sine of pi all over 6 was 1/2. But we also said sine on the unit circle, the sine function, is y. Like the y coordinate. Look at this point. Look at this point. What's my y coordinate? It's 1/2. 0.5. Okay? It is 0.5. Now watch. What is cosine of pi all over 6? Cosine of pi over 6 is adjacent all over hypotenuse. So radical is 3 all over 2, all over 1, because that's the hypotenuse. But this reduces down to radical 3 all over 2. Well, what's radical 3 all over 2? Let's do square root of 3 divided by 2. Well, that's 0.866, Mr. Carlson. Yeah, you're absolutely right. It absolutely is 0.866, which is exactly my x-coordinate, which is exactly what we said, because cosine on the unit circle, no matter what the theta is, it's going to be x, which is this, x, which is radical 3 all over 2, which is that, which is this. Are you starting to make the connections here? Okay, this is the connections I need you guys to make. And as a teacher, I can't force you to make the connections. I can only lead you to make the connections. So I hope that you're actually trying to make these connections. You're trying to follow along. I hope you're not even writing anything down. Don't write anything down. Just make the connections here. Okay? Make the connections, because that's what I'm trying to make you do. I'm trying to force you to make it. Right? So what are we doing so far? So far, what we have said was cosine of any theta angle on the unit circle is x. Sine of any theta angle is y on the unit circle. Okay? Now, what if I wanted to find tangent? Tangent of pi all over 6. Tangent of pi all over 6. What's tangent of pi all over 6? Well, it's going to be, opposite over adjacent, of course. So 1/2 all over adjacent, which is radical 3 all over 2, which means this is 1 all over radical 3, which is radical 3 all over 3. Okay? Radical 3 all over 3. Great. What did you just do here? What's 1/2? That's sine, right? So sine is 1/2. So what we could have just done was sine of pi all over 6 divided by cosine of pi all over 6, because that is my quotient identity. Verbatim. Usually what we do is just tangent of theta equals sine of theta all over cosine of theta. Well, what if we have the theta? What if the theta is pi all over 6? Then that means sine of theta all over cosine of theta. What's sine of theta? In this case, pi over 6. What is sine of pi over 6? We said 1/2. Okay, 1/2 right here. Boom, 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 boom. What's cosine of pi over 6? Okay, great. Radical 3 all over 2. What is that? Boom, 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 boom. It is still sine all over cosine, which reduces down to this. Now watch. Let's erase some of this stuff here. We said tangent was y all over x. So 1/2, 0.5 all over 0.866. Ready? So let's do that. Let's do just 0.5 divided by 0.866. Okay? So that's 0.5773. Now let's erase some of this. That's 0.5773. So what is square root of 3 divided by 3? Is it the same thing? It is. It is. I hope you're following along. I hope that you're not just tuning me out and just be like, I'll write stuff down and I'll actually learn when he's done. I'm teaching you what you're supposed to be learning. Okay, you're supposed to be learning right now. Okay, this is what you're supposed to be learning, the connections. You don't understand how big the unit circle is in mathematics. It's almost as big as E equals mc squared. It's almost as big as Newton's law of cooling, and it's almost as big as Euler's beautiful formula and the Pythagorean theorem and so forth. Like, this is something that's really big in the mathematical age. And I can't teach you trig. I can't even remotely think that you'll move on without learning what I'm teaching you. Okay? So pay very close attention. Now, what if I make this 30-degree angle, not 30 degrees, what if I make it 45? Okay? So now, 45 degrees. Think about it. Okay, this is pi all over 4, right? That's 1. That's 1. And we said this is radical 2, correct? Yes, Mr. Carlson, that's correct. That's what we said at the very beginning of 2 weeks ago, 1 week ago, 5.3a. Basic trig functions and special angles. Yes? Yes, that's right. Now, what if my r is 1? Is this r right here 1? No, it's not 1. How do I make it 1? I have to divide by radical 2, of course. That will make it 1. But if I divide by radical 2 with the hypotenuse, I need to divide by radical 2 with everything else. And if I do that, what happens then? Well, that becomes radical 2 all over 2, and this becomes radical 2 all over 2, and this becomes 1. Which means, what do I have now? What I have now is pi all over 4, okay? And this becomes 1. This is radical 2 all over 2, and this becomes radical 2 all over 2. And they are isosceles triangle because it's 45, 45, right? Now, if we say sine is our y in our unit circle, what is sine of pi all over 4? Well, look at it. Sine of pi over 4 is radical 2 all over 2 divided by my hypotenuse, which is 1, which is radical 2 all over 2. But sine is y, which means it's this. So 0.707. And if we go over here, what is the square root of 2 divided by 2? 0.707. Okay? That's what it is. And even if I do sine of pi over 4, which is 45, I get the same thing. It's the same thing. Why? Because it works. The unit circle pulls this all together for us. That's why we have the unit circle. Okay, and I could do the rest for cosine of pi over 4, which I will just really quickly. Cosine of pi over 4 is, of course, radical 2 all over 2. Okay, I'm going fast, obviously. Radical 2 all over 2 because it's adjacent all over hypotenuse, but it's the exact same thing. And then if I do tangent of pi all over 4, that's going to be sine all over cosine, radical 2 all over 2, divided by radical 2 all over 2, which is 1. But it's also 0.707 divided by 0.707, which is still 1. Right? So now what we're doing is we're getting away from the acute angles, we're getting away from the right triangle trigonometry, but we're putting the triangles on the actual xy plane, and we're literally following these angles however they turn. We're following these angles however they turn. So now, what if I wanted to do 60 degrees? My other special right angle. Okay? And so now what I can do is build this. So this angle is 60 degrees, so pi all over 3. This is radical 3. This was 2 and this was 1. I don't want 2 right here. I want 1 because that's my radius for a unit circle. So I divide by 2, which means I divide by 2 here. I divide by 2 here, and that gives me 1. Right? So that means what I have is 1 right here, radical 3 all over 2 right here, and then 1/2. What is sine of pi all over 3? Sine of pi all over 3 right here is literally just my y-coordinate, or opposite over hypotenuse. Opposite all over hypotenuse is radical 3 all over 2 all over 1, which is radical 3 all over 2, or it's just my y-coordinate. What's my y-coordinate? We already saw that 0.866 is radical 3 all over 2. Okay? And then cosine is my x-coordinate. So cosine of pi all over 3. What's my x-coordinate? 0.5. If I wanted to do it on my triangle, 1/2 all over 1, which is 1/2, but we already know it's 0.5, which is the same thing as 1/2. Are you making the connections here? I hope you are. I hope you're actually thinking. Okay, think. That's what math is for. You're thinking. You're supposed to be thinking now, okay? So these are my special angles on what we call the unit circle. Now, let's actually bring back the circle here. Okay? Now, if I make that 90 degrees, I get this. If I make it, let's just say 120, I get this. Another 30 degrees, I get 150. I get that. Another 30 degrees, I get this, 180. Another 30 degrees, I get 210. Another 30 degrees, 210's right here. Okay. Another 30 degrees, I get 240 or 260. Another 30 degrees, I do get 240, but I want to get to in between here. Okay. So if I just go down 225, I get this. But from 240, another 30 degrees, I get 270. Another 30 degrees, I get 300. Another 30 degrees, I get 330. Right there. And another 30 degrees, I get 360. What did I just do? I went 30 degrees all around each quadrant. What it's going to look like is you're going to see something like this. And you can make triangles out of all of it. But there are special triangles within each quadrant. The 30, 45, and 60 degree triangles, right? Correct? There's special triangles within each of it. But they all correspond to each other. So what will that look like? It'll look like this. And this right here is the full unit circle. I was so proud when I put this picture on here. And then now you can actually see that it follows all the angle measures, all the points, everything. Okay? And you're probably thinking like, what do you mean, Mr. Carlson? What do you mean? I'll show you what I mean. Let's go to 45, 45 degree triangle. So right here. Oh my gosh. 45 degree triangle. Look what I did here. Look at that. Isn't that beautiful? Perfect line. Okay, it's straight perfect. Now, my 45 degree triangle, we said, okay, with this triangle, this was a radius of 1, radical 2 all over 2, and then radical 2 all over 2, which means my x right here is, right here, radical 2 all over 2. It's kind of hard to see. Okay, if I shut off the label here, I will. There you go, radical 2 all over 2. And then my y right here, radical 2 all over 2, is right here. Make sense? Perfect. Okay? And now if I erase that and then we go to, let's just say, the opposite side. So if we follow this down, if we follow that angle all the way down, and then we see 225. So now what we can do is let's just go to the opposite side, 225. So right about there. Okay? 225. I can still build my triangle there, right? If I wanted to. I can build all the way right here, my triangle, right here. This is my reference angle, pi all over 4, because 45 degrees is in between 225 and 180. 180 plus pi over 4, or 45 degrees is 220. Now, this will be, watch. This is where it gets really interesting. This will be negative radical 2 all over 2. And this is negative radical 2 all over 2. And then this is 1, because my radius is 1. And now notice the negatives. And notice my y-coordinates. And notice my x-coordinates. Okay? So it's negative radical 2 all over 2. And negative radical 2 all over 2. And also notice this. If I want to find tangent, I take my y, negative radical 2 all over my x, negative radical 2 all over 2. And then that becomes 1. Because negative divided by negative is a 1. Now watch this. All students take calculus. Is your tangent right here that we just did, tangent, y all over x, this is y, this is x, y all over x, is that negative or positive? It's positive. Because even all students take calculus connect together. It's brilliant. It's beautiful. It's amazing. Okay, notice how all your x-coordinates right here in the cosine quadrant, they're all positive. Notice how in the first quadrant they're all positive. Notice how here your y-coordinates, your sine, is all positive, and then right here everything's negative because only tangent is positive. It's so beautiful to me, and it should be to you. And I hope it is. So, what did we just learn? We learned a lot of things, and it's really difficult, even as a teacher, to kind of summarize everything that we learn in a concise whole. The best I can possibly do is for you to just literally play this video, play that, and just see how it just connects, and just study it. I can't teach you, okay? I can't teach you I can only teach you what the things are. I can't necessarily teach you how they work because that involves study. And unless you study this circle, how it relates to the triangles in here, then you really never will fully understand why we have a unit circle. Okay? I can try to teach you why, I can try to teach you the what, but how we have a unit circle, that's really hard, okay, to do. So I hope you study it a little bit more in your own time. I'm going to pause it right there. I'm going to go back here. And now what we're going to be getting through is our actual lesson. That was our lesson, but we're going to be applying the lessons, the unit circle, in a more concise way. And really, we're going to be applying it with domain and range. We're going to be looking at sine and cosine functions. And then we're also going to be looking at periodic functions. Okay, so domain and range of sine functions. I'm actually going to go through this really, really quick. The next couple slides, I'm going to actually go through really, really quick until we get to what we call periodic functions, and then we're going to apply reference angles, and then we're done. Okay, so domain and range of the sine and cosine functions. The cosine is going to be negative infinity to positive infinity. I'm going to show you that literally later. I'm going to show you that tomorrow. And then the range of these are going to be -1 to 1, -1 to 1. Okay, so this is what the domain looks like from -1 to 1 for the cosine. And then for the range for sine, it's just going to be -1 to 1 as well. You don't really need to know this too much. This is really important for when we get into the graphing functions, and that's going to be tomorrow's video. I just wanted to show you that though for right now. Now, review of even and odd. Your algebra teacher may or may not have went through what we call even and odd functions. They're actually pretty easy functions. The reason why I want to review it algebraically is because even and odd functions apply to trigonometric functions as well. So let's just say I have, for example, y equals x squared, and I want to algebraically put in a negative x. If I want to algebraically put in a negative x, what makes it an even function is if I get that same function out. The exact same function that I started with, I get it out. What do I mean by that? What I mean by is if I plug in negative x right here into the function x squared, so negative x and then squared, well, negative x times negative x is going to be a positive, but x times x is still positive x squared. So nothing really changed. So since it hasn't changed, what we call this is what we say an even function. Okay? That's an even function. Why is it even? Well, look at the squared, guys. So that's probably the easiest way. It's what we call an even function, okay? Now, if I have what we call, I'm going to erase this. Now, if I have what we call an odd function, it's almost exactly the same, but something slightly different. And that is if I have, let's just say, a cubic function, and I plug in a negative to test it. Okay, if I have a cubic function, I plug in a negative. So negative x, plug in a negative. So I have this. Now, if I take negative x times negative x times negative x, yeah, those go poofy. The x, not the x's, but the positives. And then, though, I still have a negative x. So I still have a negative, and then x times x times x, which is x cubed. Is this the same function I got back? No. The function I started with was a positive. This is a negative. So it's a different function, a negative right here. Okay? That's what makes it odd, and also because it's cubed. Okay? Trig functions can be even and odd as well. What does that mean? Let's find out. It means that even and odd trig functions allow us really then to know which values will be negative and which values will be positive even before we put it on the xy plane, even before we evaluate it. That's crazy, okay? That's really crazy, all right? So what does that mean? Well, these are my functions, my definitions. We really don't use these that much. So if you're getting overwhelmed, like this is a lot of formulas, honestly, guys, we really don't use these this much. To be honest, to be perfectly honest, I don't use them that much, okay? Now, there are some questions on Math Excel. By some, I mean like probably like 2 or 3 on your homework that will literally ask you to go through the even and odd trigonometric definitions, okay? But in all honesty, we really don't use them that much. And by that much, I mean after this slide, I'm not really going to be introducing them ever again, okay? But you will probably have one on your test. You will probably have one on your homework quiz and a couple on your homework, okay? That said, the only even trigonometric functions are cosine. That's the only even trigonometric functions. Pretty interesting, to be honest. And you're probably wondering, like, why is that? Well, think about it. It's the second in line, sine, cosine. Okay, that's 2. 2 is even, and then tangent. But not more mathematically. That's kind of just like kicks and giggles. More mathematically, the reason why it's even is because, remember, it's a cofunction of sine. Okay, not cofunction. I don't want to confuse you. It's not the cofunction of sine. It's a co-captain. There you go. It's a co-captain of sine. It's a co-angle of sine. It's not the cofunction of sine. It's the co-angle of sine. So if you have an angle, one angle, sine, if you have a co-angle, that is like kind of your double pal. That means you're even now, okay? I had a math teacher explain it to me like that. It made sense, so I hope that makes sense to you. That's the only reason why it is therefore even. All the rest are straight up odd. So what does this mean? It means if I'm given something like this, cosine of negative 45, if I already know that this negative will therefore make it into a positive, this therefore equals just cosine of 45 degrees. And then I can evaluate it as such. So radical 2 all over 2. Now, what is actually cosine of negative 45 degrees? Cosine of negative 45 degrees actually goes down. Okay? And this would be pi all over 4, and then you would evaluate it as such. This would be in our normal triangles, not our unit circle triangle, but our normal triangle, this would be 1, negative 1, and this would be radical 2. And then my adjacents would be 1, and then all over radical 2, which rationalizes to radical 2 all over 2. But notice this is the fourth quadrant in which cosine is positive already. Cosine is positive already, so therefore that's what makes it what we call even. Okay? Now tangent, since it's an odd function, what this means is it's going to be negative tangent, following my formula here, negative tangent of whatever that angle is, pi all over 3. Now, pi all over 3, what that is you can look on your unit circle, you can look on the trig table of common angles, or you can evaluate it just by using, pi all over 3. Your triangle, if this is pi all over 3, this is radical 3, this is 2, and this is 1. Okay? Right? That's where pi over 3 is, the first quadrant. Okay? And then tangent is just your sine all over cosine, or your opposite all over adjacent, so radical 3 all over 1. So this is negative, and radical 3 all over 1, which is just radical 3, but you still have a negative chilling there because there's a negative inside, and following my trigonometric even and odd functions, you have to put the negative outside. So with odd functions, you put the negative outside, and then with even functions, it just completely goes away, as we did here. I'm not going to teach you more on the even and odd functions than that. It is pretty interesting. And like I said, Mathexo will kind of go through it just a tad bit. Okay, but you don't really need to spend too much time on even and odd functions. Okay? So let's move on to the main event, the periodic functions. What are periodic functions? I already kind of did it during bell work, guys. Periodic functions really are just sort of those functions that recycle over and over and over and over again. By recycle, I mean they repeat. They are repetitive, okay? They have a pattern. Okay, just like seasons, winter is a periodic season because it occurs every 365 days. Same thing with summer, okay? Cycles when you're on a bicycle or even a car, your tires repeat over and over and over again to its flat rate, essentially, the RPMs, the miles per hour, and everything. Okay, and also women also have a periodic function in their bodies to tell them of certain sorts of just baby producing things, reproduction. Okay, that's why we call it a period. That's why we call it a periodic function. It repeats. That's why that's what it means. Okay. So, what does it mean in trigonometry? If it means that in seasons, it means that in reproduction, if it means that with cars and everything, what does it mean in trigonometry? Okay? What it means in trigonometry is that they repeat every 360 degrees or 2 radians. Why is that the case? Okay? Because they repeat every 360 because they're nowhere on the circle are they undefined. So what we're going to say is that they're not undefined at all. They're not undefined at all. That's what we say. Now, this is true for sine and cosine, but is it true for tangent and cotangent? Sort of. Instead of repeating every 360 degrees, they repeat what we call every 180 degrees, or pi radians. Why? Because there are trig functions, specifically tangent and cotangent, in which they're undefined at certain values. And they're undefined at every multiple of pi all over 2, or what we call 3 pi all over 2. They're defined, undefined at every multiple of pi all over 2 and 3 pi all over 2. How do I know that? Well, if you allow me to, go back to your trig table of common angles. This is your trig table of common angles. I know it's sideways, but just bear with me. Look at tangents, okay? Look at tangent. So tangent's right here, and it's undefined at pi over 2. Why is it undefined at pi over 2? Because look at sine and look at cosine. I know it is, you kind of have to bend your head a little bit. It's lopsided, but just look at sine and cosine. Sine is 1, cosine is 0. What's tangent? X all over y, or sine all over cosine. So if tangent's sine, which is 1, and cosine all over cosine, which is 0, that means it's 1 all over 0, which is undefined. Okay? And then it repeats every pi units, essentially. So what does that mean? It repeats. After that, it is now undefined right here. Okay, another pi units. If I take pi over 2 plus pi, which is 180 degrees, or in other words, if I take 90 degrees plus 180 degrees, 90 degrees right here plus 180 degrees, I get 270, which is 3 pi over 2, which tangent is now therefore undefined. Okay, so sine is negative 1 all over cosine, because that's tangent. Negative 1 all over 0 is undefined. So these things repeat over and over and over again. And we'll explain more about that tomorrow when we go through the graphs. But I wanted to show you that right now. What does that mean for us? With periodic functions, the periodic properties of sine and cosine, it means this. So if I have sine of some angle, I can take and separate that angle into what we call the periodic function of 2 pi. Okay, I can separate that angle in the periodic function of 2 pi, and then whatever is left over is my actual angle that I'm interested in, the sine of t. We did that during bell work with a cosine of 31 pi all over 4. Okay, and same thing here with cosine. We can split that angle into the periodic function of 2 pi, and then whatever angle is left over is the angle that I can evaluate. And if we're looking at tangents, I can do tangents of t then plus pi. Okay, I can split it up in an angle of pi, and then of course that would just equal tangent of t. Okay, now I don't think we're gonna do any tangents here. We're only gonna be doing these. Okay, so cosine of 420. Now we could build this, go around the circle, and then be like, find reference angles and everything, and do it that way using the xy plane, or we can put it in radians and then counts, right? That's usually how we do it. But let's do it a little bit faster in that there is a periodic function of 360 degrees in 420. So watch this. Following my formula up here, okay, this is 360 degrees. What do I need to add to 360 degrees in order to make it 420? What do I need to add? I need to add 60 degrees, correct? So if I add another 60 degrees, it makes 420. Now, per my formula, this right here is the periodic function. I don't need to evaluate that. I already know it repeats. But what I do need is this. So that means what I really need to solve for is just cosine of 60 degrees, which if we use our unit circle, it is 1/2. Okay, cosine of 60 degrees, if we use our unit circle, if I go back, use my unit circle or my trig table of common angles, cosine of 60 degrees right here is 1/2. Okay, cosine of 60 degrees is 1/2. Highly encourage you to print that off. Just saying. Okay. Now this one right here, let's go to sine. Now this one's a little bit more tricky, but we can still do it. Okay, so that means sine. How many times does 4 go into 9? Twice. What's 4 times 2? 8. So this is the same thing as 8 pi all over 4. Okay. But then I still have a pi all over 4 left over. This is 1 pi all over 4. And 8 plus 1 is 9 pi. So I can split it up like that, correct? And I know 8 pi all over 4 is 2 pi. So this is the same thing as saying sine of 2 pi and then plus pi all over 4. And as per my formula right here, okay, do I really care about the 2 pi? No, I only care about the pi all over 4. So I really only care about evaluating pi all over 4, which of course using my unit circle, using Desmos, using just my basic right triangle special angles, I know sine of pi over 4 is radical 2 all over 2. Okay? Hope that makes sense. Let's erase. This was a rather lengthy lesson, but I think it's an important lesson for you guys to just understand the very foundations of what we call the unit circle. What did we do? We did a lot. We used the unit circle to define trigonometric functions of real numbers. That was the first part. Then, after we looked at the unit circle, after we analyzed the unit circle, after we made the connections between the unit circle with identities, with sine being y, cosine being x, and so forth, after we did all of that, what we then did was we recognized the domain and range, we saw even and odd functions, and then we used periodic properties. Awesome. I know this was a lot today, guys. I know this is a lot, and I know some of you are probably wanting to do retakes on your quiz and everything like that. That's available this week as well. Please prepare yourself for the homework quiz tomorrow. This now starts the third week, so now you don't need to do the homework quiz if you have an if you have an 85% or above in my class. I'll explain that during the Google Meets. But do your homework regardless. Sorry for the length, but I hope it makes sense. Replay the video if you need to. But this is C Squared Mathematics. This is Mr. Carlson. I hope you guys enjoyed the video. See ya.